Hello. I'll be talking about Lemma 2 of Theorem 16.16. Theorem 16.16 is the Lagrange's four-square theorem, which states that all natural numbers can be written as a sum of four integer squares. And let me continue with the lemma here. So the lemma statement is let n be a positive integer that is not a perfect square. Then if we're given integers a, b, then there exists s, t, u, v, which are all integers such that as plus bt is congruent to u in modulo n, and at minus bs is congruent to v modulo n, and 0 the absolute value of s, t, v, and u are all between 0 and n is less than square root of n, and s squared plus t squared plus u squared plus v squared is greater than 0, which just basically is saying that not all of them are 0. Okay, so let's go over the proof here. So we're going to consider the set of ordered pairs as plus bt minus u, comma at minus bs minus v over here. And we're gonna, remember always that a and b are fixed right here, and it's only that s, t, u, v are moving. So we're gonna let s, t, u, v move from 0 to the floor function of square root of n, which is basically the greatest integer less than or equal to square root of n. But square root of n is not an integer, so. Okay, so let's continue. So here we can see that the number of types of ordered pairs of as plus bt minus u, comma at minus bs minus v is the floor function of square root of n plus 1 to the fourth power. Well, because st and uv all have that many choices to the to the fourth power, right? So this number is less than or equal to n squared because this inequality holds. So this product is less than n is greater than n squared over here. And just one thing, even though the values of this may match, we're gonna count them differently for some reason. Okay, so since this is n squared, you know that ordered pairs, so we're gonna consider modulo n over here. You can choose for ordered pairs in modulo n. There are n choices for here, and there are n choices for here. Therefore, there are a total of n squared possible choices in modulo n. Therefore, since the number of types of ordered pairs is greater than n squared, we can use Pigeonhole's principle that there will exist integer quadruples s1, t1, u1, v1 that is not equal to s2, t2, u2, v2, such that these two are congruent in modulo n, and which is saying that some of them, because this is greater than n squared, some of them will kind of like concur. And because this holds, because there exist these kind of integers, we can rewrite this as the following. And we're going to set s as s1 minus s2, and t as t1 minus t2, and u as u1 minus u2, and v as v1 minus v2. And here we can already check that the first two conditions over here, match the original one, and these ones are obviously matched, as this implies that none of s, t, u, or v can all be 0. And secondly, since we picked from this range, there are s, t, u, and v are all in this range. So both conditions are satisfied, so that proves our result.